I'm glad to have you back. Today we're going to be discussing force and friction. Here's a copy of our equations thus far. Today we're going to learn what is Newton's third law. We're going to learn how to draw a free body diagram, differentiate between static and kinetic friction, and we're going to learn how to calculate friction. Newton's third law. Newton's third law is when a force is exerted on an object, that object exerts an equal and opposite force back. For example, headbutting a door. Um, I'll use this example in class quite often with students, but if you go up to a door and headbutt it, you're going to feel a force on your head. Well, how do you feel a force on your head? Because the door, when you headbutt it headbutts you back basically with an equal and opposite force directed on your head. This exact same spot that's exerting the force on the door. Punch a block wall. Go up to the wall, and if you punch it, wherever you're punching it, whatever much force you hit it with is how much force it's going to push back on your own hand. Now, I don't advise you to do this, and I don't think it would be a good way to learn, but I think we can easily understand about Newton's third law this way. Normal force. Normal force is the force that is acting perpendicular to the contact point. It always acts away from the surface. So, for example, down here at the bottom, my first example with normal is I give you n equals m times g. The normal, it's acting perpendicular to the contact here, so it's at a 90-degree angle. The normal is an example of Newton's third law. It is going to act in an equal and opposite direction. So, and it's going to be equal to the weight when we're talking about something that's flat. If a 500-pound pig is standing on the ground and the ground is pushing up or has a normal force back on the pig of 500 pounds. Now, the normal on a slanted surface is not going to be equal to the weight. All right, later on, because your weight will act straight down, and we're going to talk about that probably more tomorrow. But your normal is going to be less than your weight. And if you look at the size of these vectors, the red arrow I'm drawing here is bigger than the blue one. It would actually be, if you think about it in terms of this, it would be the hypotenuse. So the weight is going to be larger than the normal force. But the normal force, what I want you to see, is still going to be perpendicular to the contact, to the point of the surface that it's making contact with. The next thing we're going to talk about here is frictional force. Frictional forces, there's two types of frictional forces, static friction, kinetic friction. And in static friction, it's when it's still. Is the easiest way to remember that. In kinetic friction, kinetic meaning movement, all right, so this is when it's moving. So the static friction is mu times n, or we just learned that n equals m times g if it's a flat surface, so we could say that F equals mu times mg. You may not like my mu there, it may not be a very good mu. Let's make that mu look a little better. I don't know if that's much better or not, but that's my mu. And that's for static. It's just something standing still. For moving, the kinetic friction, there's mu. It's still going to be m times g. It's just there's a different type of friction because we're saying it's now moving. Static friction is like when you go to move the fridge. The fridge is kind of stuck in place, and it almost pops when you move it, meaning it pops. When you first start to move it, it takes a lot more force than it does after you get it moving. It'll break free. Well, that's what's happening with static friction. The static friction is the amount of friction that's holding it in place, and once you actually get it to start moving, that's your kinetic friction. And we're going to do a lab on that that'll make that seem a whole lot easier. All right, our first problem here. Find the coefficient of friction between two objects. We have a 100 kilogram box that is sitting on a flat surface. It requires a force of 500 newtons to overcome static friction. Okay, what we've got here then is we're talking about the static friction, and it's mu times n. Well, let's start to plug in some things we know. N is the normal. That's the force pushing straight up on this box. And that right there is going to be m times g. So let's start to plug the things in. I know that the force is going to be negative 500 newtons. Mu I do not know. The mass is 100 kilograms, and gravity is negative 9.8. So in this case, mu turns out to be 0.51, and that's good because we typically are going to get a mu of less than 1. If you get a mu of greater than 1, I advise you to rework that problem. What I want you to understand is mu it's like a ratio, is how much friction due to the normal force are we going to get? How much of that normal force is being turned into friction? For example, different surfaces have different amounts of friction. There's going to be a certain amount of friction between ice and, let's say, the rubber tires on your car, and there's going to be a certain amount of friction between the rubber tires and the concrete of the road. When it's ice, this mu is going to be lower. When it's concrete, the mu is going to be higher. It just means you have more friction. It's a higher ratio. A larger percentage is being turned into friction. Okay, find the coefficient of friction between the two objects. I want you to go ahead and pause this and see if you can work this one out. As you can see here, I've given you a list, help you with your list. I'm sure one of your questions is going to be, why is the force negative here? What we got here then, I put the kinetic friction equals mu times n. N is the normal. And we said that the normal is just m times g because we have a flat surface. Alright, so it's simply a flat surface, so it would be just m times g. That will change if we have it on an incline. And we divided and got mu equals 0.41. Okay, what we've done here is I've drawn a picture up here of a sled with a rocket on it. It tells us that the rocket puts out a force of negative 1,000 newtons. And actually it's 1,000 newtons. So I'm going to actually change this. It won't be negative. And this is the force of rocket. The force of the friction, of the kinetic friction, we don't exactly know yet. So we got a couple things we're going to have to solve for here. First thing we go through here is they want us to find the acceleration of the sled. So even though the rocket's pushing with 1,000 newtons, we can't say that all 1,000 newtons are being turned into a force that's accelerating this sled. Some of the force is being lost due to the friction between the sled and the snow. So let's find out how much force is being lost, and that's the frictional force. There is a frictional force. Alright, this is the force of the rocket, and this is the force of the friction. Well, what I found out is my kinetic frictional force is negative 1,470 newtons. So I've drawn that up here at the top. It's pushing to the left in my drawing. It's negative because it's opposing the direction it's wanting to go. The force of the rocket engine is 1,000 newtons. So I've got that up here. It's pushing to the right. My net force, alright, when you put these two together, the net F of n is the net force is negative 470 newtons. Well, now I get to find the acceleration. I know my net force. So F equals m times a if I want to find the acceleration. So now it's just a matter of substituting in what I know. My net force is negative 470 newtons equals the mass of the sled. Solve for the acceleration. Hey, as we come to find out here, the acceleration turns out to be negative 0.63 meters per second squared. We'll talk more about this in class tomorrow. I hope you've learned a lot about friction. It is a force. It does cancel out some of the force. It can be turned into stopping force if it's a friction of a car trying to stop. It can increase depending upon what the two surfaces are. That is directly related in our equation by the mu. If mu is high, it's probably something like rubber on concrete. If it's low, it's probably something that's on ice or something that's slipping very easily. Hey, I hope this has been fun for you. I'll see you on the flip side.